So good afternoon. Okay, Brian?
Yeah, good to go. You can hear you.
Okay,
Yes.
okay. Hello, everyone. It's my great honor to be a first speaker in CSR 2021. I'm Li Hui from the University of Electronic Science and Technology of China. So here, my presentation will be divided into two parts. The one is review of the main liquid rocket engines development in China, and the second is the turb pump fault detection algorithms based on SVM. In fact, China has made great progress in space activities in the past 2020. For example, Chinese space activities have grown rapidly, whose launch activities accounted for the 1/3 of global launches. In the deep space exploration, the Tianwen-1 is planned to land on Mars in May this year, and then the rover carries out inspections and other works. China has also succeeded in developing a new generation of launch vehicles. For example, the first flight of Long March 8 is meaningful for the development of our country's low and medium orbit satellites. All the launches missions are based on the powerful thrust of rocket engines. The development process of Chinese liquid engines is divided into 3 stages. In 1970s, China began to develop the Long March 2, 3, and the 4 vehicles using the storable propellant engines as the main power units. Because of the limited launch capabilities and propellants toxicity, China began to develop cryogenic propellant engines and high-pressure staged combustion rocket engines in the 1990s, and the main power units of Long March 5 to Long March 7. Since entering the 21st century, China has begun making advanced research on the HAV launch vehicles and their propulsion system, and has confirmed the development of large thrust liquid rocket engines. For the first stage, the main type of YF-20, YF-40, and YF-47-75. The first two belong to the storable propellant engines, which has lost one of the cryogenic propellant engine. These 3 types of engine, which have successfully performed more than 300 launches, stand as the cornerstone of the great success in the past. Here is the spectrum of Long March 2 to Long March 4 and their main power units. YF-20, the main engine of the conventional launch vehicle, is a gas generator cycle engine. It is not only used as a booster in single engine configuration, but also used in the first stage where quad engines are connected, and in the second stage as a single engine with variants. And Long March 4 launch vehicles adopt this storable propellant engine YF-40 and is modified in the third stage. The Long March 3-8 adopts a higher performance YF-75 in the third stage, where it is composed of 2 independent engines. For the second stage, the main type of these 4 engines, the first belong to high pressure state combusting HPSC rockets engine, while the last 2 are cryogenic propellant engine. These 4 engines have different meanings to the development of Chinese liquid engines. The first type is Chinese first oxidizer-rich HPS rocket engine. The second one is the first HPS engine and the engine. Okay. Here is a spectrum of the new generation launch vehicle and their main power units. The four new types of engines have improved Chinese launch vehicle technology based on significantly enriched the Chinese launch vehicle system and will contribute to launch vehicle regeneration and become the cornerstone of Chinese space industry in the future. And the recent progress of Chinese main power units are focused on the new generation large thrust liquid rocket engines. The first two are the main power units for the future heavy launch vehicles. The third type, TQ-12, it is the liquid oxygen methane engine, which is reusable and has ability to insert propellant. These three types of the engine may meet the requirements for the human lunar landing, other space programs in extensive space accesses in the future. Next part, I will introduce one of our past work, turbo pump fault detection algorithm based on SVM. With the development of the aerospace technology, the space carrier is increasingly complicated and its working environment is extremely limited, so it is easy to cause security issues. The engine is part of the highest failure rate in the space carrier, as it is shown in this figure, and the turbo pump is a component of highest failure rate in the liquid rocket engine. The turbo pump vibration signal is the rapidly changing signal, and fault can usually be found earlier than slowly changing signal. Therefore, the fault detection algorithm based on vibration signal is an important aspect of the research on turbo pump fault detection technology and system, and it is great importance to reduce the loss of the turbo pump failure. The research started two turbo pump fault detection SVM algorithm based on the time domain features or frequency domain features. SVM is widely used in general linear classifier to do classification. The decision boundary is the maximum margin hyperplane for learning samples. It can be used in lunar separatable and non-separatable problems. For the linear separatable problem, the sample can separate by hyperplane H. Directly, here is the decision classification function fx and the decision value. Well, for the linear non-separatable problem, the sample can hardly separate it correctly, so we use the generalized optimal separating hyperplane H to describe it. For the linear non-separatable problem, the method mentioned above can't solve it completely. We can map samples to high-dimensional linear feature space and the constructed linear optimal separating hyperplane in this space by using an appropriate kernel, like this. The data comes from the Hausen vibration acceleration signal of a certain type of liquid rocket engine turbo pump historical test. It contains two groups. Each group of the signals includes 3 test signals. Other basic information is shown in the table 1. The first method is based on the fast SVM and time domain features. It has 2 parts, training and test. As for the training part, its purpose is to construct the decision classification function by the training data set. The first step is to choose this first step, fault track as the training data, because of the fault track includes the normal and the fault signals. Okay, the second step is to extract the data to ensure the number of the normal step equals to the fault. Then the third step is to determine the sum step size and segment the data preparing for calculating each segment's time domain features. Then the fourth step is to determine the time domain features. We calculate each segment's time domain feature and combine them into a feature vector. These training samples makes up the original training sample set. The number of the original training samples is large, so we need to select the boundary training samples to meet the real-time demand. We calculate the distance between a normal sample and a fault sample by equation 9. If the distance is non-linear, equation 10 can be transformed into the equation 11 by KCPT. Then we get the distance matrix D here. Showing in equation 13, it is transformed to the linear matrix D by finding the normal and the fault samples whose distance is the smallest. So we connect T star is the boundary training sample set. Those size is much less than the original, and the number of the normal samples and the fault samples in the boundary set is balanced. So the last step of the training part is to train support vectors and construct decision classification functions. Anyway, as the test part, the purpose is to test whether the model above is feasible or not, and check the system's accuracy and timeliness. The first step is to choose another track, as the tested data normal track is used to test if the system will alarm by mistake, and a fault track can test whether the system will alarm in time. For the second step, the sixth step is directly related to the speed of the cycle detection and the accuracy. If the step is too large, the system may not alarm timely. Well, the step is too small, it may influence the effect of the alarm strategy. Based on the experience, the test step is determined as the 4000s. The next two steps is prepared for the construction the test sample set based on the same time domain features. And then we classify the test sample set by the decision classification function. The normal one is 1, where the fault one is -1. So we can get screens made up of 1 and -1. Then it comes to the alarm strategy, which is to determine whether there is a fault in the test step based on the screens. We choose the multi-index weighted alarm strategy. The index includes the number of the one in the screens and the max number of the consecutive one. The calculation formula of the alarm value is shown in equation 16. The last two steps are used to judge whether the system should alarm or finish the test. The above is a test part of the first algorithm about the turbo pump fault detection. Before showing the results, here are some basic information. We choose the fault track 1 as the training singles. The length of the normal and the fault segments is both 2 seconds. The sample step is set as 100 and the test step is set at 4,000. So the length of the classification result screens is 40. As we mentioned above, the training speed is too slow because of too many original training samples. So we use fast SVM by selecting the boundary training samples. The training effect is shown in table 3. So as for the fault track 2, the system didn't alarm on the normal working condition and it alarmed in the time interval, including the fault after 250 seconds. Alarm value rose rapidly and went beyond the threshold when it was earlier than the shutdown time. Other tracks results are listed in the table 4. The system didn't have the false alarm in all normal tracks. Well, it also didn't have the mission alarm in all fault tracks. 2 false tracks alarm time is significantly ahead of the shutdown time of the original system. The above is the first method, but there is no obvious boundary between the normal state and the fault state of the turbo pumps, which is a continuous change process. So it improves the shortcomings that the classification results of the traditional SVM is to absolutely by constructing the fault membership function to reduce the risk of the false alarms. The flow chart of the second method is almost the same as the first, but there is still some difference. The first difference is that the second method is based on the frequency domain features. The fact is that the frequency domain status of the test signals have obvious difference before and after the fault occurs. Fault track 1 is taken as the example. We can use from the features that there are 3 main frequency components in the normal signals spectrum map. Well, there are 4 in fault signals, so the standard diversion of the spectral amplitude is determined to the frequency domain features. Fault track 1 is taken as an example. We can see from the figure that there are 3 domain frequency components in the normal signals spectrum map, where there are 4 in fault signals. So the standard diversion of the spectrum amplitude is determined by the frequency domain features. The second difference is to construct the fault membership functions to force the fault classification result 1 of the traditional SVM into the fault membership degree 0 to 1 represents the decision value of SVM. The last difference in the test part after calculating the membership degree of each fault sample, the system compares the membership degree with the misclassified threshold if its corresponding sample is regarded as the misclassified sample. Its classification result is turned from 1 to 0. Then we can get a screens made up of 1, 0, and -1. Also, some basic information is listed in the table 5. The time of the normal and the fault training signal segment is both 1 second because of the way of the constructing the training sample set and the step. The number of the training samples is reasonable, so there is no need to select the boundary samples. The detection results are shown in the figures. We only show the detection results of the normal track 1 and the fault track 2 because of the space limited as shown in this figure. We can see that there is no wrong alarm or missing alarm. Also, the system alarm earlier than the shutdown time. Other tracks results are listed in the table 6, which show that the algorithm meets the accuracy and the real-time demands and can ensure the system alarm in time. Based on the experiment result above, both two algorithm activities, the accuracy and real-time demands to meet the design requirements, and the second algorithm can control the false alarm risk by calculating fault membership degrees. So that's all my presentation. Thanks for listening. And any question?